In this video, we examine the type of intermolecular interaction that is called dipole-dipole induced. These dipole-dipole induced interactions follow naturally from our studies of ion-ion interactions through Coulomb's law, ion-dipole interactions, and then dipole-dipole interactions in the gas phase and in the solution phase. Okay, so let's talk about generalities of the dipole-dipole induced interaction. Okay, so suppose you have a molecule that does not have a charge, so it's not an ion, and it doesn't have a dipole, okay, which means that it's not polar. Okay, so that may be something like nitrogen. Okay, so nitrogen 2. N2, which we can draw simply as NN. Again, because the two atoms have the same electronegativity, there's not a negative end, there's not a positive end, which means this molecule doesn't have a permanent dipole moment. However, something that could happen is that if you bring a molecule that has a dipole, so for example HCl, okay, here you have a negative end, and here you have a positive end. An idea is that, this nitrogen molecule actually has an electronic cloud, okay, which we can describe using molecular orbital theory, for example. And the idea is that that electronic cloud can actually fluctuate. Okay, so a potential thing that could happen here is that, the presence of this negative charge right here, of this tiny partial negative charge, might actually induce a motion of electrons towards that end of the molecule. Okay, and if those electrons of the molecule tend to end up in this end, then what happens is that temporarily, okay, you induce here a tiny little negative charge, which means that this end of the molecule will have a tiny little positive charge, and under those situations, now you're actually going to be able to interact attractively with HCl. Okay, so again, N2 in general would not have this temporary dipole moment. Okay, the presence of a dipole moment near it might induce the temporary dipole moment that can facilitate an attraction. Okay, so that is the concept of an induced dipole, okay, caused by the presence of a dipole moment. Okay, all right. So now, how do we actually codify? How do we quantify this ability of a molecule or an atom to deform its electronic cloud to have or to present a temporary dipole moment? Well, that is the concept of polarizability. Polarizability is the ease with which a molecule or an atom might deform their electronic cloud to be able to have an induced dipole. Okay, and you can see how the polarizability should depend on how fluffy the electronic cloud of that molecule or atom would be. Okay, so for example, if we think about the periodic table and we look at the halide atoms, okay, what should happen is that, because you have many more electrons as you go down the periodic table, the polarizability of this atom should be actually smaller than that and that. Okay, and that is actually true. If we think about relative polarizabilities, okay, so the polarizability of these with respect to that and these with respect to that, it turns out that the polarizability of chlorine is about 3.9 times greater than that of fluorine, and the polarizability of bromine is about 5.5 times greater than that of fluorine. Okay, the same thing would happen for molecules. Okay, so for example, if you have methane, okay, which is a tetrahedral molecule, methane is apolar. You will have dipole moments in each of these bonds, but they will cancel each other out geometrically. And then if you compare that molecule with this molecule, which is carbon tetrachloride, okay, well, now you actually have many more electrons. Okay, clearly, the electronic cloud of this molecule can be much more easily deformed than the electronic cloud of methane, and that means that the polarizability of this molecule is much, much greater than that of methane. Okay, so with this, we're actually ready to see how the equation that captures this interaction between a dipole and an induced dipole, how they take place. Okay, so the equation is going to be potential is going to be equal to something important here is that what you have in the denominator is going to be 4 pi E naught and then R to the 6th. Okay? And then in the numerator you're going to have the dipole moment squared, okay, times the polarizability. Okay, so that is how you capture this. Okay, so the interaction of, say, a dipolar molecule like HF, okay? We have a negative end and then a positive end, okay, is going to be equal to the dipole moment of this molecule squared, which is what we have right here, multiplied by the polarizability, which again is this alpha term, and that depends on the ability of the electronic cloud of this apolar molecule to deform in the presence of an external dipole moment. Okay, very important as well is the fact that this distance also depends along the inverse 6th power of the separation between the dipole and the molecule that is apolar. Okay, so this is another of the van der Waals forces. Notice that this is actually a very short range force. If you separate this dipole moment from the molecule by just a little bit, okay, this term has such a high power that means that the attraction is going to decrease really, really rapidly. Okay, so again, as you move down this list, you can see that, well, as you go from ion-ion to ion-dipole to dipole-dipole to dipole-dipole in solution and then dipole-induced dipole, what happens is that those forces, while they're still attractive, they become increasingly shorter range. Okay, they disappear really quickly as you separate the two species that are attracting each other.